Hello, this episode is going to be gravitation and gravitational fields. Right, so I want to start off with gravitational fields. So, for gravitational fields, we've got our first fact, which is going to be a force field is a field where a body experiences non-contact force. We've then got, in gravitational fields, we have Newton's laws of gravitation, right? So, first of all, we've got the gravitational constant, which is known as capital G. That's going to be 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. And then we have our equation for Newton's laws of gravitation. And this equation is going to be F equals gmm over r squared. So that means that F, which is the magnitude of our force, equals the mass of our first object times the mass of the second object times our gravitational constant all over a distance between those two masses squared. So that there is the Newton's laws of gravitation equation, right? So we've then got our force acting on two masses are equal and opposite. So that means that we have a force acting on from the first mass to the second mass, and an equal force acting from the second mass to the first mass. And the distance between those two masses is going to be r, right? So next up, that is gravitational fields, Newton's laws of gravitation finished. And then we're going to move upwards, and we're going to move upwards towards our inverse square law. Right, so inverse square law is going to be that this applies for the law of gravitation. So it means that F, which is the force, is proportional to 1 over r squared. Which means, for example, if we double the distance, our force experienced will increase, right? So we've then got our diagrams. So what we have is our field diagrams. So we have a object, and this object is going to be our planet. Let's call it E for Earth. Then we're going to have lines, and we draw these lines going into and through the object mass. So we draw lines going across, all the way around. So basically lines sticking out, and these lines need to be perpendicular to the tangent at that point. So essentially they need to be sticking directly out of the actual object itself. But we need to make sure that these lines are not actually going through the planet, because these lines are supposed to come off of the surface of the planet, and that's how we represent it when we're doing a diagram. So we've got the lines of force will all meet at the center of the planet. We've got the mass will be attracted to the planet due to the field lines of the force. So what we want to do is we want to draw the arrows going into the planet, because with gravitation, our force is always going into the planet. And then we've got our M. So we've got a mass. So to find out where they are, we can put a mass within the field, and then wherever that mass is going to move, it's going to move towards the center of the planet. So it's going to move towards the center of the gravitational field, which will also be the center of the planet. So that's how we work that one out. And then we've got, if we move a mass further away from the planet or the gravitational field, the gravitational force will decrease. So this is because our field lines are further apart. So when we drew our lines coming out of the planet, our lines are now going to be further apart than they were when they were coming straight out of the planet, because essentially the lines are going to be spreading out, and that's exactly the same as the force actually felt on an object that's in that field. So that now is that gravitational fields part of the gravitation and gravitational fields topic. So we're then moving on to orbits and satellites. Right. So let's start off with orbits. So we've got an orbital period and speed. So we've got the force equals the mass times velocity squared over r. And we've also got another equation in orbits, which means that F equals gmm over r squared. Now that equation was previously listed by myself in the gravitational fields topic. So we can apply both of those equations and put them into each other. So we can essentially equate the two equations because they're both equal to F. And then what we do that is we rearrange for V. So both equations, F equals mv squared over r and F equals gmm over r squared, we will set mv squared over r equal to gmm over r squared because they're both equivalent. So once we've equated those, we can find V. Now, once we've found V, we know that V is equal to root gm over r. So that's our next derivative equation. So we can derive that equation, V equals the square root of gm over r, from our two force equations. Right, so we've then got an elliptical orbit. In an elliptical orbit, our energy will keep changing between kinetic and gravitational potential energy. Right, so we've then got our satellites. So as for satellites, a smaller mass that objects a larger mass. So essentially this means when we have a large mass and we've got a smaller mass, this smaller mass is going to be in the gravitational field of the larger mass. So it's going to, if it's going to be attracted to it, essentially. It's going to have a centripetal force toward the center of the larger mass. Right. So it's kept in orbits by the gravitational pull. So if we have a velocity that's perpendicular to the centripetal force, we're going to have circular motion, obviously, but the centripetal force, it's important to note that the centripetal force in this circular motion is the gravitational field of the larger mass, right? So then we've got speed is equal to circumference over time period. So that's a very important equation for finding another proportionality equation, which is t squared is proportional to r cubed. Now we can find that from the speed and the circumference in the time period, which means that the larger the radius of the orbit, the longer the time period. Right, so that's satellites. We then have our escape velocity, which is the minimum speed an object needs to escape a gravitational field without any more force applied to it. So our equation for this we're going to use is a half mv squared, which is the kinetic energy equation. And we're then going to set that equal to gmm over r. So that's the gravitational constant times both masses times together over the r, which is the distance between the masses. And we can then work out from that our v. So our speed, our escape speed. So our escape speed is going to be known as VE, which is equivalent if we get those two sides and we equate for V. So what we're going to get is we're going to get V equals root gm 2gm over r. So that's our escape velocity. So essentially what's going on with our escape velocity is we need a amount of EK, or kinetic energy, and we need that kinetic energy to equate or be at least the amount of potential energy to escape the field. That's what we're looking for there. So we've then got R, and R is the distance from the center of the planet to the object. Right, so that's that done. We've now got geostationary and low orbiting satellites. So essentially we've got a geostationary satellite will have the same angular speed as the planet. So it's moving at the same angle per unit time as the actual planet, the satellite is. So we've then got synchronous orbits, which is the next type of orbit, which is where the orbiting period is equal to the rotational period of the planet. An example of this is geostationary satellites. So that's pretty much the same thing. So that means that it takes the same amount of time to do a full rotation as the planet does to take a full rotation. So we've then got a low orbiting satellite. This is classed as a low orbiting satellite only when the satellite is between 180 kilometers and 2,000 kilometers away from the actual planet itself or the larger mass. So that's above the surface as well. Note, because it's only classed as a low orbiting satellite when it's between 180 kilometers and 2,000 kilometers away from the center of the larger mass. Sorry, not the center, the surface of the larger mass. So you'll need to add the radius to find the distance from the center there. So what are some benefits of low orbiting satellites? Well, they're cheaper. They are used for mapping, spying, and imaging due to being close. They need much less powerful transmitters due to them being closer to the planet. However, due to their speed, because they are so close, they're going to have a very high angular velocity. So we're going to need more of them. So because of the fact that they have a very high orbital speed, we will need more low orbiting satellites, right? So we then have gravitational potential. This is the amount of energy potential that an object acquires at a point in a gravitational field. We then have our equation, which is V equals minus gm over r, where g is the gravitational constant, m is the mass of the object in the field in kilograms, and the distance from the center of an object in meters is r. And we always have a minus because potential energy is negative. V is potential energy, which is in this case gravitational potential energy per kilogram, measured in joules per kilogram. We then have gravitational potential is negative on the surface of a planet, and then it increases with distance from the mass. So it's actually negative when we gain it, but if we talk about having positive energy when we lose it, this is because work is done when we move an object from a point of higher potential or higher field strength to lower field strength. This means that we need to give energy through work done, because work done equals energy transferred. Now, because we have the energy transferred, this means that when the mass is at an infinite point away from the gravitational field, we're going to have zero. Now, if we're transferring energy towards zero, that means that when we're at the center of a gravitational field, we're going to have a negative value for potential energy. We then have our gravitational potential energy, which is for this graph that we now have. And our graph that we now have is going to be a V over R graph. So essentially, it's going to be gravitational potential energy over the radius of a sphere or a planet or a mass. But we have to assume in this case that it is round. So for the graph, the gradient of a V over R graph at a tangent on that graph, the gradient is minus g. So, at that distance from the center of the sphere, we find minus g by doing v over r. So essentially finding a tangent at that point on the graph. So we then have our equation for this, which is g equals minus delta v over delta r. So that's basically meaning that the gradient, which is v over r, which is changing y over changing x, which is changing v over changing r, is equal to minus g. So minus g, if we want g, we can just flip times both sides by minus 1, and then we've got g equals minus delta v over delta r. We then have, if we sub it into the equation, we then have our next equation, which is going to be delta w, which is changing work done, equals mass times delta v. So that's saying that the amount that we move, our work done, is equal to the difference in potential times our mass. So the energy needed to move an object between two different gravitational potentials, g's, is the gravitational potential difference. If we sub in the equations into each other, so if we sub both of these equations, which are those two, we get EP, which is the potential energy, gravitational potential energy, equals minus GMM over R. Now that is given in the data sheet. That's all for gravitation and gravitational fields.